Good afternoon, everyone. Welcome back to the session 2 of our day 6. Today we have Mr. Anmol Krishna Sachdeva for the session 2. It is our privilege to welcome Mr. Anmol to this FTP on Agentic AI. Anmol is a senior solution engineer and hybrid cloud architect at Google with deep expertise in generative AI, MLOps, cloud-based systems, and AI agents. He holds an MSc in Advanced Computing from the University of Bristol, UK, specializing in artificial intelligence and machine learning. With his unique blend of academic excellence and practical industry experience, we are delighted to have him with us today. Please join me in warmly welcoming Mr. Anmol Krishan Sachdeva. Over
Thanks.
to you, sir.
All right. Yep. Thanks for the introduction. I'll start sharing my screen.
Yes.
All right. Fine. So, firstly, everyone, a warm welcome from my side. Thanks for joining this session. Over the next 2 hours, we'll be going. All right. I'll start again because it just got started. All right. So, thanks for joining, everyone. Over the next 2 hours, we'll be having a discussion about one of the critical topics in AI ML field, which is called observability. This particular topic is going to be, I would say, spanning beyond the general AI ML related discussions. We are going to get into the operational side of things and understand what exactly constitutes observability. This particular public repository has all the notebooks that we are going to use today, and the notebook has been created the primary notebooks have been created by keeping in mind that we will be using open source and zero sign up kind of tools. So we essentially won't be having any kind of uh, registrations or credit card signups, etc. required. Do feel free to post your questions in the chat box. I have put the link to the repository in the chat box for everyone to see. If you want to follow along and have a computer right now, you feel free to even follow along. And the labs are pretty straightforward, so you won't require any additional setup as such. They will work regardless of which operating system you are going to use. The way the repository is arranged, I'll just tell you. So we have a folder for Docker. This particular directory has some files related to Docker Compose and Prometheus related setup. If you want to go with Docker setup or Prometheus setup for exporting the metrics and trying out things, there are instructions written here, but primarily we will be focusing on the main logic. This is just an additional thing for which the readme and the follow-up instructions are provided, so you can try as a take-home exercise post this session. Then there is a directory called notebooks. Here we have 4 notebooks. So first we'll be starting with the overview, and then we will be going through the remaining 3 notebooks. The first one will be focusing on the logging, the second one will be focusing on the tracing aspects, and the third one will be focusing on the metrics aspects of the same. And primarily, this is how our remaining 2 hours would be looking like. We'll be going through first understanding how the traditional observability differs from observability when we talk about LLMs in general, and then now advanced agents that we are working with. Then we will be getting into a bunch of theoretical concepts, followed by some lab exercises related to logging. We will also be focusing on some of the other aspects than regular observability. So we will try to touch upon the FinOps aspects and the GreenOps aspects as well. And then we will be getting into distributed tracing. Again, we'll be making use of a tool which can be set up locally without any kind of credentials. Then we'll be getting into the metric side of things. We'll be also covering some additional things like how profiling works, how alerting works, how you can leverage the thread dumps or heap dumps, etc., in different scenarios. There is no dedicated, I would say, lab as such for the last topic, which is around the governance, topology, and security aspects. But we'll still try to cover and get back to the leading practices that are there in the industry for such kind of things. And then ultimately, we will open for question answer session if we have time. And just as a note that any of the things that I'm going to discuss are going to be from my own personal experience, so don't relate them to my employee or any organizations that I'm associated with. So this is pretty much kind of a disclaimer for all the exercise that we are doing as part of this particular talk. Everything that we have is pretty much open source and should not be related or associated to any of the companies. Let's get started then. I'll move to my uh, IDE, and then we'll get started with uh, basically lab one. So, in general, when we talk about observability, most of the people have limited view of what observability means, and that's why we have to move away from the traditional AI ML lens to a general SRE lens, I would say. How a site reliability engineer thinks of observability. And that's where we need to understand that it is not just about logging, it is not just about only having some sort of metrics populated and seeing fancy dashboards in Grafana or some other visualization tool. It is more about having an understanding of the health of your ecosystem. When I say health of ecosystem, we can understand it as health of how your servers are performing, health of how your upstream downstream ecosystems are performing. And when I talk about upstream downstream ecosystems, I do mean that any kind of APIs that you are interacting with, whether they are healthy or not, what if they are not healthy, how would you be mitigating the issues that are going to be introduced because of them not being healthy, whether you will treat your service as healthy if some API that you are dependent on or a database that you are dependent on goes down. And similarly, when we talk about the clients which are trying to access your agents or the systems that you have developed, to them, whether the performance is decent enough or not is also a question. So sometimes it happens that you may say that your servers are working fine, but the clients might not be having the real performance delivered. It might be because of some issue that lies between the client and server interaction track, or it could be that your servers are producing the responses, but then some huge payloads are there which are taking time over network to get back to your clients. Or it could be that you have not really implemented the right set of practices. Like, I'll give you a basic example. In traditional let's say web solutioning, what we do is we implement caching of images or static content wherever we think it would make sense and the content won't be getting changed frequently. Even today we are able to have the caching done for dynamic content, but the principles for caching differ between static content and dynamic content. Similar cases for the AI use cases. Here we don't have to literally think in terms of the binary content being cached. Rather, we have to think in terms of the semantic context of the call. So let's say we have a query, why Earth is not flat, and we have another query, why Earth is round. So for both of these queries or prompts that we are going to feed to our system, we are going to receive the similar sort of responses, because naturally the answers will be very much aligned. It's just about us asking the questions in different formats. So that's where most of your answers will have common context, and hence they will have a higher degree of semantic similarity. And hence we could probably have one answer cached and served to all the prompts which are semantically similar, then going ahead and doing cycles and computing the responses, making calls to tools or resources, and then computing and giving back the response. So that's where it's about not just logging. We need to understand at the server side and at the client side what all things really matter. When I talk about server side, we certainly need to have logs with respect to what our server has been performing, what kind of interactions have been happening with any of the upstream downstream systems, even to the extent of understanding the authorization, authentication, and identification related aspects. So, whether clients are making calls to your agents are authenticated, authorized, or not, that also essentially is covered under observability. So, observability is not just about application logging. You have to think from security perspective, you have to think from overall ecosystem perspective, and it also these days boils down to not just tracking the system health, but also tracking what on the financial side the burnout looks like. So if you are spending, let's say, $10 million just for running some agents, which could have been served using more, I would say, better technical patterns, etc., it certainly should be a concern from observability perspective as well to you, that okay, your budgets are exhausting. And when we talk about running resources in areas which are not using green energy, so probably you could be having data centers that are powered by coal supply and are not running on solar panels or wind energy, then in that case, certainly it does make sense for us to rethink and choose data centers which are certainly abiding to the data regulatory requirements, like jurisdictional requirements. If your data center needs to be in Europe, and it needs to follow, let's say, GDPR compliance, then it is following. But within Europe as well, wherever we can have the greener energy sources, we go about them. So logging, monitoring includes metrics, then tracing, which is about the life cycle of your whole transaction and the nested calls that are getting made. And then anything to do with FinOps, anything to do with the profiling of your code, be it CPU profiling, memory profiling, thread profiling, whether deadlocks are there or not. Sometimes it happens that your agents keep on going into infinite loops and they don't really respond, and that's where you have to analyze whether it's a memory issue or whether it's a deadlock issue, etc. All those aspects are pretty relevant. Then coming down to how much of carbon emissions your agents are essentially producing, because emissions are not really related to the training loop. Many people think that when we are training the AI ML models, then that is where the actual carbon costs increase, the footprint increases. That's not really true. Inference is a pretty hefty space when we talk about the carbon emissions, and hence we have to think about the carbon footprint and the FinOps aspects as well. So throughout these three different labs that we are going to go through, we will be having logging, monitoring, tracing, profiling, FinOps, and GreenOps aspects all covered. And that's where you will get, I would say, a view of a comprehensive observability stack that one should be setting up ideally for their workloads. There are going to be some uh, aspects related to tracking of the underlying data and its propagation, etc., tracking of related things like data lineage, correctness, etc. Those will fall beyond this particular talk scope, but we will be slightly touching them as and when it's appropriate to bring up those topics. All right, then. So far, in case you don't have any questions, I'll go ahead and move with the presentation. I'll just see if there are any specific questions posted in the chat box. All right. I'll get back to you with the messages that you are seeing sometimes. So invalid notebook message, when you are seeing, is it like specifically about a particular notebook? Okay. Think I'll need to reload one of my notebooks. Okay, I think I have outputs in my notebook, so I'll go ahead and flush them out quickly. Uh, just allow me a second. All right, so this should be sorted now. Yeah, okay, you can get the notebook cells now working. Hope it is working for everyone. In case you have any questions, feel free to again post in the chat box. Fine, so we'll go with the first one. All right. So so far we have understood that there are different aspects when we talk about observability, but what exactly is the change when we are comparing it with the traditional virtual machine-based applications or container-based applications and the LLM space and the AI agent space? Specifically talking about the AI agent space, I would be marking one difference here. Originally, when LLM started, they were more or less stateless. We had single run kind of completions. When I say single run completions, for people who are new to the terminology and all, they can also follow me by looking at the cursor where I'm pointing. So LLM applications traditionally started with the stateless single turn completion kind of status, wherein you could feed in any prompt, and then there will be no memory or no lookups or no I would say loops as such, which will go through any of the tools, etc. And you will get a kind of response which will be a one time response, and then that particular response will be discarded because ultimately there are no memory related lookups that are going to happen. But as AI agents have evolved over the last 2 3 years, there are now memory based loops that are there, so we call them as stateful execution loops. And these particular stateful execution loops help us do things like plan and solve, or reason and act. So you would have heard the term react probably in this series already from some other lecture, but this is more about you typing something on a prompt interface, and then the prompt interface going ahead and trying to think about what this could be. So I'll just give you an example. We'll open a kind of prompt interface, any random one, and we will say uh, how much time does it take for uh, hydrogen ionization to happen in a reactor. So I'm just putting a random kind of prompt here, and you would see that there is this activity that is going on, and it will start expanding. It says I'm defining the scope, and then it will start getting into a bunch of loops. It is telling, calculating ionization times and all. You will essentially see a breakup as well in some of the prompts, wherein it will go ahead and it will start spitting out this, and here it will show the thinking output as well as to how it thought about, etc. So that is where we essentially have this react phase coming into picture, wherein what behind the scenes is happening is that we are having some tools. There could be database calls, there could be API calls, there could be some sort of augmentation that you might be doing by grounding your search with the data that you have in your enterprise context, etc. And that is where there are these thinking loops. Once we get the responses from these tools, we essentially have the AI agent controller think whether it has got the convergence done or not, and then go about again kind of checking the tools if at all there are any other invocations pending, or it requires more time to have the convergence condition met. And specifically throughout this, what is happening exactly is that you have your agent which is making a call to a third party system or a local system. Now this particular call will be going over network or will be done locally. Again, there will be some latency for sure, or network hit. And then it could be that the third party system that you have is further taking some time because it might have some other dependencies that it might be calling. So it could be that if it's a synchronous operation that is happening, which generally happens with such kind of use cases, you would be having execution time of the third party system influence the overall thinking time for your system as well. And that's where when we are talking from observability lens, we need to understand whether our system is underperforming or whether the other system is essentially having any critical issues. It could be that the third party API, let's say API ABC that you are going to hit, that ABC API is having some downtime, or could be having degraded performance, because of which your calls also have started to get into degraded mode. So it's a dependency because of which your performance is getting hampered, rather than your LLM itself, the agent itself, the main controller having any issues. So that's why, in order to trace which service is culprit or where exactly the time is going, you need to have for a single transaction a kind of an end-to-end trace that needs to be there, going through all the function calls, etc. And every function call that you're making is adding to the cost, because there is some computation in your data center that is there is some sort of power usage that is there. So both at the financial side and the economical or climate side, you have some sort of contribution. And then when we talk about kind of green operations, or the time it takes for inferences, etc., to happen, many times you would have seen that you have the prompt essentially respond very quickly, but then after a couple of iterations, you might just have this particular line spit out from the console, and it might be taking a lot of time to spit out the rest of the phrases, or the sentences or paragraphs. This is also something which could happen because of the load that is there on the system, or because they have not got the right inference architecture, or they might be treating the key value pairs in a very different manner. Like, those are the aspects that we'll be getting into shortly. So, as part of this particular lab, we are going to have the following learning objectives. First, we will be understanding how we can have the structured output logging done using kind of general tools that are available. Throughout this particular talk, we are going to focus on Python as the programming language. Given that we are working in Jupyter notebooks, it makes it easy. However, it is very important to note that whatever patterns we are discussing here are pretty much applicable for other programming languages as well. So you are not really restricted by Python as the programming language. If you feel like going with Rust, Golang, C++, Java, whatever you feel like going with, go ahead and try to just simulate a similar kind of ecosystem, and you should be good with the experiments there as well. We are going to have some wrapper functions written just to record the latency, maybe have token usage, cost usage, aggregations, etc. Highlighted. We are also going to use a specific library called Code Carbon, which actually gives us an offline aggregator. This offline aggregator will actually be checking how much of power during the execution time is being consumed on my local machine. But when you go ahead and try this out in a cloud ecosystem, it will actually be checking where the data center supply is coming from. It's a solar power supply, or whether it's a coal power supply. Then how much load is there in the electricity grid for that particular data center, whether it's a green data center or whether it's a non-green data center, where that particular data center is located. Some of the tools like Code Carbon also have network call related hops also covered as part of the analysis. So there are tools and ecosystems that are available. We are just using some select ones because they are applicable on the local runs as well. So Code Carbon is one of the libraries which will be giving me the power usage related stats, and hence I'll be able to compute how much of carbon emissions from my set of runs that I'm going to execute today will be. And then ultimately we will go ahead and we'll have the cost aggregations and the carbon footprint aggregations directed in the log, so that we can see how things look like. First thing that you need to do as part of this whole lab is that you just need to ensure that you are running in the Python virtual environment. So there are instructions in the README as well available if you got a chance to look at it. So for now, like, there is a virtual environment that you can create, and there is a requirements.txt file that you can download. I have a similar kind of thing available as part of the inline Jupyter notebook installation. So I'll go ahead and I'll try to have the dependencies installed. Just before the session, to keep it short, I actually had the dependencies installed. So for me, it shows as required requirements already met, but for you, it might be downloading some libraries. It may take like 3-4 minutes if you are on good internet connection. So and just make sure that you catch up once this particular thing is done. So traditionally, your applications have such kind of application logs, wherein you are putting the log level, you are putting something related to user tracking, etc. You are also putting some kind of message, and then you are trying to have the timestamp, etc. Now, this from traditional logging systems and applications look pretty okay. However, one issue, me being, let's say, a person who has to extract some information or filter the logs, will be finding this really inconvenient. So a better thing is to have it in some sort of a structured format. Many of the log management servers essentially support JSON based logs. So such kind of a log statement can actually be converted into a JSON log, so that you can go ahead and you can ask questions directly in your log management servers, because they will be doing indexing on this particular data. So you can ask questions like, what is the average cost of user 123? Now, many of the log management servers have already started natural language prompt based querying. But if you are not doing a prompt based querying, then also you can very well filter on where the user id equal to user 123, or you can do a user id regex match 123 and so on. So such kind of log management servers do exist, and they have been in production for almost all the enterprises that are working. You might have kind of worked with Kibana, Elasticsearch, Logstash based systems, or Grafana Loki and all. So all those are good examples of log processing systems which have index based stuff. So that's where, like, first goal for us is to convert our log statements into such kind of structured logging, so that we can have some outputs which are filterable, and which can be kind of parsed by the log management servers, even through the NLP prompts that are going to be fed. So what we are going to use for this particular lab is, we are going to use the structlog library. This is a Python library that offers us with the clean JSON output. And exactly what is happening here is that we are going ahead and importing some of the important libraries. Structlog is one of the important libraries, but then there is a local mock of LLM that I have done, which actually has the client simulation and response simulation. This is just to ensure that all of you are able to run LLM kind of examples on your local without having to register against any particular provider. There is also an Olama kind of class that is written in this, so you can go ahead and check the source file once. In the source, there is a mock LLM py, and again there is an accompanying readme.md file that you can check out. So if you go through the structure of this source mock LLM file, you see the first class is the mock LLM response. This particular class essentially returns the structured response with these attributes. So you are having the actual prompt tokens getting outputted. You have the completion token count also provided to you, and then there is a heuristic based calculation of the cost that I am currently returning. Now, this essentially will differ based on the different providers that you are going to use. Sometimes some of the providers are giving the uh, token consumption results directly from their output, but when you are using things like streaming or RPCs for interacting with such kind of servers, so when you do a REST based interaction with the LLM providers, mostly you get the token completion count, etc. But when you are doing over streaming, not many of them support yet. However, like, there are feature requests with many of the providers to support token exposure over streaming as well. So once that is done, you essentially have the output token count, etc., with yourself. The tokenization logic and the aggregator logic is something that really depends on the provider. But as a general rule, like, you can go ahead and count four letters as a token, or you can go with the OpenAI standards, and you can leverage that for doing a heuristic based calculation. What I've done is I have just taken a heuristic that cost is based on $15 per 1 million input tokens and $60 for one per 1 million output tokens. That is what I'm driving my heuristic calculation with. So essentially, the cost that will be coming will be a mocked up cost following this particular logic, based on the prompt tokens, which are the input tokens, and the completion tokens, which are the output tokens for me. Then I've written a class which is the mock LLM client class. Again, this is to simulate a client side kind of API, and this is essentially again for lab testing, just to make sure that it matches the real world sort of configuration. I have introduced some sort of random latency and jitter to it, so that not every time we are having a static sort of response. So every time you'll be seeing a different response when you run this particular class. And for now, as I mentioned, like, I'm taking an average compression of 4 characters per token. You can kind of choose some different methods as well if you like. And I have got a couple of prompts for which, based on conditions, I have given the response text with thought and action to simulate the React loop. So I am specifically asking for population of a particular country, and if there is a question which is asked for multiplying that population by X, then essentially we get the response. So this is the simulation of a React loop that I have done in my local itself, so that I don't have to really call an LLM and see the responses. Everything is being done locally for this particular simulation. Likewise, I have a bunch of questions related to quantum computing and so on, and ultimately I'm returning the response text, the prompt tokens, and the completion tokens. So naturally you can assume that we will be calling the LLM response class for sure to get the cost attribution, etc., when we have such kind of computation happening. There is a class for Olama client as well that we have kept here, and it's again having good readme, so you can follow along and understand. If you are able to download any model, generally the download takes time, so I've kept it outside the scope of this particular lab. If you are able to download a model, then you can go ahead and you can very well utilize this. There are instructions in the readme as well to leverage the Olama client class. So coming back to our structured logger, this is where I introduce you to the mock LLM interface that I have written. This will be ensuring that we are able to stub sort of the responses and the class calls. And then we have the code carbon offline emission tracker kind of getting instantiated later by using this particular library. From structured logging perspective, we are configuring the logger with the log levels, which is natural. We are having the ISO standard timestamper, and we are having the JSON dictionary format getting used. And we are just mentioning that the context class is going to be dict, which means the underlying data type is going to be dict for holding the log context keys. We are just making sure that the logs are able to get spit out in the standard output, and we just ensure that the logger that we are creating is actually cached so that we can have some performance overhead avoided. So we'll go ahead and we'll execute this particular thing. We see that we have our logger initialized now with JSON logging. This is just an example of a test log. We see that we were able to set some keys like status equal to success, version equal to 100. Again, like it's a structured logger, so you can pass the key value pairs. Those key value pairs don't need really to be hard coded, so you can have new keys also added, and that's why you are getting a functionality of dynamic logging, which will be pretty good when we talk from production perspective, given that in production systems, when we are generating JSON logs for sure are much more in size than the regular logs. We can see here that the JSON log is pretty big than the regular log. So many people start reporting when they move towards JSON logging in production that okay, they are hitting now their logging budgets because uh, their applications are emitting more logs in volume. And earlier, let's say if the log volume was hypothetically 1 TB, now after doing JSON, it's 2.5 TB. So that's where one needs to understand that log filtering is also a concept that one should be applying. And then dynamic logging means that if at all a key doesn't exist, or let's say a key should not be existing because you are not able to find a value, you simply don't pass the key. If you pass the key, then you are just passing a value like an empty string or a null value, etc. Like that is unnecessary and introducing payload overhead. So in the new age log management systems, you already have filters for such kind of things. If the key doesn't exist, you just filter the log. So it's pretty much like existence check, like you have semi joins in databases and all. So that's the concept how it works with. So you really don't have to put a particular key if that doesn't make sense for a record, and that's how you go ahead and trim down your log size as well. Okay, so from local prerequisite perspective, you just need to ensure that you have gone through this mock LLM Pi. If you want to use the Olama client, then there are separate instructions in the README that you can go through. And essentially, we'll be having the simulation of inference done. We'll be having the cost attribution and the carbon emission attribution also factored in. So this is the first kind of script wherein we are doing all these kind of uh, uh, functions, or the goals are being met. So we are having the configuration of the offline emission tracker done. we are having the execution of the LLM call done. Eventually, it calls the functions that we have written, which allow us to get the attribution against the FinOps and CarbonOps aspects. And then we get a logger which has the FinOps and carbon footprint related readings mentioned. So what we do is we first instantiate the class object, and LLM client is what we are using. Again, like the code has a lot of comments for you to self kind of evaluate what the code is doing. If you want to make any changes, feel free to do so. But I've introduced type hints, and also that you can follow along and understand the expected structures. Um, and you essentially are making an LLM request, and here you are just specifying the loggers. You are having the offline emission tracker kind of initialized or configured for your carbon tracking. There is a timer that I have put. Like this is a naive implementation that I'm showing to you. In production systems, generally you will be using something like decorators. There are generally decorators available. If you are using Prometheus and all, and you are using open telemetry, there will be decorators available that will time the function on its own. So I'm not sure how much familiar the people here are with the decorators, but you can very well go ahead and do an iterate something like decorator function, whatever is the name here, and that will do the trick. So you will just need to ensure that the library through which you are having the decorator imported, which has the functionality for doing a timing or injecting some trackers or observability related functionality are imported. So you can just go ahead and leverage decorators. For now, I'm using a naive man sort of implementation technique, which is just doing a start time and time and taking the difference between the same. So now we are having the tracker start. Now tracker start essentially is starting the tracking for the carbon footprint. We are having the LLM response by putting a prompt, and this is just a function. So prompt is essentially being fed as a parameter to this. And we then have the latency by doing current time minus start time, just to ensure that once the prompt has been fed and the response has been received, we are able to time. And then the emission kg also is when the tracker stops. Now there could be questions as to, okay, this particular time function is also being tracked from a tracker perspective, etc. So that's where when you use decorator, you can define the order in which you want to calibrate the kind of findings. And then ultimately you are going to have the logging done with the values. So we are just going to have the structure like token input, token output, etc. put, and we are going to read from the response variable here, which received the response for the class that we defined. So if you go back to a class LLM response, we were having if we see, we were having the text, prompt token, completion token, and cost attribution. So that's where we are reading the prompt token, completion token, cost, and the text. And the text we are truncating to 60 characters, so that it's kind of a snippet of the prompt that was sent, and nothing much more get exposed as such. There is exception handling as well in a lightweight manner. Again, this is not a production ready code, so this is just for handling the use case here. If you go ahead and see this, the function has been instantiated. So now is the time for us to simulate the user sessions. Just before getting into simulation, I would like to call out here that when we talk about response preview, now sometimes it could happen that the prompts that you are receiving have some sensitive data or personally identifiable information, or could be some health record related information, which ideally should not be logged into the log management servers. That's where there are some data loss prevention or sensitive data protection or redaction related tools available. So tools like scrub or there is something from Microsoft in open source called Microsoft Presidio. There is Google sensitive data protection as well available in Google Cloud. There are some other tools as well. I think Nemo guardrails is also present. So such kind of tools you can leverage for doing a data loss prevention. And there are some more aspects to such kind of tools wherein you can sanitize the input and output responses, and also identify OWASP threats like jailbreaking attacks, etc. So that is beyond that discussion is beyond the scope of this particular talk, but you might have had some taste of that discussion in some of the sessions. And just for this particular laboratory, we are keeping the truncation logic as the logic to restrict the text, but in general you would be having some sort of sensitive data protection, or some sort of data loss prevention, or log redaction logic using some sort of library getting used, so that your credit card information shows as a sequence of X characters, or your email shows as a redacted thing, or if at all there is a sensitive information which needs to be present there, it is shared like some API key, etc. Then it is a SHA, let's say 512 hash that you have. So there are techniques of hashing or redacting or obfuscating, like different libraries have different kind of uh, uh, behavior that you can go through. So, what exactly we are trying to do here is we are simulating log generation for the mock LLM prompt that we are going to feed. So, first prompt is explain quantum computing, and the second prompt is what is the capital of a particular country. And we are just ensuring that we are feeding in user ID and session ID as two attributes, so that we can have the tracking done based on these. And when we go ahead and execute, you'll start seeing that it really is a function of how much time my jitter logic is putting when these responses come. So basically, first record shows that what the prompt was when we fed the input to the system. So it just had a question, and the event type was LLM generation started. Log was info type, and we essentially see that there were no tokens reported. But then in the response output, we see that the latency was reported as 1.4 seconds. Again, this is because of the jitter that I have added to simulate production scenario. We see that the token count is essentially being reported as 10, and the output prompt is output token count is 45. How it is 45? This is the response that we got. So it is converting to 45 based on the 4 character per token sort of logic that we had. Cost attribution is being driven by the 15 million per one dollar 15 per 1 million token for input tokens, and then dollar 60 for 1 million tokens for output tokens. So that cost is coming out to be around 0.002 USD for this particular call. The CO2 emissions essentially is a function of the latency that is there here. So sometimes, like if I rerun this particular thing, it might be that the smaller prompt essentially is taking more time. Okay, we were able to simulate that. This is just because the time being taken by the smaller prompt here is more because of probably some dependencies, etc. So one crucial thing that you need to understand here is that even if your token count is high, aggregate token count is high for a particular prompt cycle, it might be that the carbon emissions for the prompt having less number of tokens is more, because of the time it takes for the computation to happen in the background. And this is a pretty kind of critical observation for people to make, because people generally will go with the notion that okay, I have 5 tokens that I am putting in my system versus 50 tokens, so the computation for 5 tokens ideally should be faster, and hence less resources should be getting used on my machine. But it really is a function of when you are scheduling, what's the electricity grid usage at that time, whether the data center is running on non coal resource, like any green resources or coal resources, or any kind of resources which are not renewable sort of thing. And that's where the carbon emission gets tracked. So it might happen that even for smaller tokens, you might have bigger CO2 emissions. And that's why when people start tracking their carbon emissions, they get surprised a bit when they see such kind of results. And that's where it has to be uh, taken through some analysis over a period of days to months to understand where you exactly fit, whether you need to change the routine or when your jobs run. Because many times there are websites also, like there is electricity grid website, and then there is a time watt or something kind of website. I have linked those resources. Those websites tell you the data center grid usage stats. So they tell that okay, this particular data center is running free in the night, or it's running free at 2 p.m. in the afternoon, etc. That way, for your workloads which can actually be run at any point of time in the day and don't really necessarily need to run at a particular cron, those can be scheduled to run at the times when the carbon emissions are seemingly going to be less. So that's kind of something that you can think through as well. Again, that's a far-fetched goal for any system to achieve, but people are investing in this particular area, so you should also be giving a thought when understanding this from conceptual perspective and then taking it into realization. All right. So with this, we get to the production guidelines and practices that one ideally should be following for such kind of setup, wherein logging, observability, etc. are there. I have already mentioned about the sensitive data protection related tools that are there. So you can configure them. The libraries, many libraries are open source, as I have already called out, and the links are there. And one thing you need to understand is that when you do the log writing, it needs to be an asynchronous task rather than synchronous writing to the system, because anyway, like synchronous writing at scale doesn't work. Second thing is that when you do asynchronous log writing, you can have your log management servers actually leverage harvesters as the clients at the side of generation. The harvesters can batch your logs and then send out the batches and even retry the batches. So that's kind of a good setup. So that's generally done by running some dedicated agents, log scrapers, or log pushers at your site. So people who are aware with Kubernetes ecosystem, you can actually run the daemon sets for log pushers. They actually will have some harvesters run which will aggregate, let's say, which will sweep the logs from the file system. Let's say you are using log rotate d as well, which is kind of a functionality which rotates the log files that are there in the file system in a particular directory. Let's say you don't keep more than uh, 5 records for a particular log during a particular duration. Such kind of settings you can set. Some of the logs, if you don't set the rotation configurations in the right manner, may end up getting missed as well, because they might not be getting picked by the log management server. So you have to be pretty cautious about what you do with respect to your log management infrastructure. But generally, a dedicated daemon with some sort of cleaning capabilities at the file system is generally preferred when we talk about logging at this scale. I have already talked about the dynamic log volume and the volume management, so you don't really necessarily need to put all the keys and just put dummy values or null values or some identifiers which you will be ignoring. Just not putting the key itself also works these days with the log systems, because they are indexing on the keys. And ultimately, from production FinOps perspective, you need to ensure that you also have some guardrails. Like, this goes beyond the observability topic, but still it's a production practice, so I'm generally discussing with you. Your APIs are very much subject to exploitation and manipulation. Even internally, you don't really need to be always scared with the external exploiters. Even people who don't understand the ecosystem or probably having some malicious intent internally could also exploit your system. So rate limiting your APIs and enforcing quotas on the APIs is generally treated a good practice, and this will certainly have impact on your logs as well. So many times, even for non AI ML systems, the problem has been that the developers they shoot up the uh, request to a level, like they do stress testing, or they do a lot of JMeter based or locust based performance testing against actual endpoints which are having even debug logs or info logs getting logged. And your systems are resilient because your systems can have that much of traffic volume entertained. However, your log volume is increasing behind the scenes. So you need to ensure and put guardrails as to how API rate limiting works for different SDLC environments. Like, how it works in the QA will be different from how it works with the production. QA will be having debug logs turned on, but production doesn't really need to have debug logs turned on, because it's generally considered noise. So such practices also you need to really focus on. Observability is not really about AI observability as such. Observability is about mostly how you treat systems to be working in a state which is eventually going to help you lower down your cost, uh, track your let's say footprints on different parameters, and understand whether the system is running healthy and within the limits or not. That's what the sense of observability is. It's really not very special for AI/ML system. It's just that some of the techniques that we use could be different from the traditional ones, but largely speaking, observability is something that is not very different for AI/ML systems as such. Just a bunch of more resources need to be tracked in some different manner. uh, so that's where I was talking about semantic caching as well in the beginning of the session, wherein I gave you an example of why the earth is not flat versus why the earth is round, yielding the same set of inputs. So why not have one response cached and then that provided to the user? And that's where we have semantic prompt caching related implementations also available in open source. There is something called a GPT cache that you can leverage, which is a decent implementation. Or you can go with vector databases like Chroma or Milvus, or there are some other vector databases, Pinecone and all, which are available. Or if you are on a cloud provider like Google Cloud, you can go ahead and use their vector search, Vertex vector search database, etc. There are different mechanisms through which semantic prompt caching can actually be implemented. You can do a local implementation as well, as I mentioned, using vector databases. It totally depends on how you want to do, but not all use cases will be relevant for semantic caching. So when it is about the text payload, etc., they do make sense, but also only in scenarios like there is a question answer system wherein you want to implement this. Now, implementing semantic caching on a text use case wherein it's about some retail customer booking their flights, etc., it's not really going to make much sense, because it's a transaction that is happening and it's not going to be semantically similar to the one that is going to be conducted by n number of other users. So there are use cases wherein semantic caching makes sense, there are use cases wherein semantic caching won't be making sense. So you have to really understand how you should be applying the different systems and controls that are available to even curb down your uh, costs, or any kind of other impact that you are looking forward to. Uh, Coming to the guidelines for production when it comes to green ops, you can certainly follow these electricity maps and what time related open source APIs that are available. This is what I was referring to, wherein you can understand when the data centers are essentially running on marginal carbon intensity, and you can also see when the data centers are operating at high. Now, what exactly happens behind the scenes from data center perspective is that when the data centers are already loaded a lot, generally they have to switch gears and they have to get to kind of switching their power supply also sometimes to serve the load. So it might be that your data center was running on solar energy, but then due to surge in the requests, your data center has to switch to a dual mode, like natural gas plus solar energy, or totally to the coal energy. That's where the carbon intensity, production, etc., also take a turn. And essentially during high intensity periods, generally for even your less number of tokens, you would be yielding more footprint. So that's kind of a correlation and causation analysis that you can go through for your set of data centers. But again, like, this is something which people will do in their mature state. It's not something that you start with on the very first day when you are writing agents, because then at that time your goals are not uh, kind of climate impact, etc. Your goals are more towards solving the requirements for the different clients, and making sure that the business requirements are being met with the right set of technical equipments that you can exercise. All right, so with this, there is a wrap up of lab one, and I'll switch to the question section and see if there is anything which you want to understand. Uh, See, going, so there is a question from an attendee whether I should go with Python C++ or I should go with Rust because it's performance oriented. See, Performance engineering is the goal when your business goals have been totally met via your technical solution. If your solution has been put uh, already, it is working fine for customers, that is when you start thinking about the performance optimization. If you put performance optimization as the first goal, you probably might have delayed solution delivery, and also it might be over engineering and over optimization kind of aspects that you might be getting into. So general rule of thumb is get the things working with a stack which can be maintained within your organization, because it could be that rust is something that you as a developer has you have learned just because you wanted a performance oriented delivery. But then there are 500 developers in your organization and none of them understand rust. Now what if you leave the organization? Like, we are talking about something which is beyond what we actually had in the session plan, but still, like, it's a question, legitimate question, which people should be understanding. So don't pick a stack which cannot be maintained by your organization. Pick a stack which you can have your organization trained on, but pick that only when you have to really make a technical choice and performance is a bottleneck for you. Like, there are asynchronous jobs which really won't be hampered if it takes like 30 more minutes, or 1 more hour, if they are not critical reports to be flushed at a particular point of time every day. But there could be tasks, as I mentioned, which are mission critical, for which the report delivery has to happen before, let's say, 12 o'clock every day. And for that you might go with performance optimization, and hence the AI system which might be doing some sort of report interpretation or optical character recognition from, let's say, documents, and then preparing a report. That particular AI task certainly needs to be written in performant manner. So first, if you have implemented that in a manner which is already kind of meeting your business requirements, you are able to ship that before 12. Then you can start thinking about the performance given your team skills. So that's how we approach generally. What alternative to JSON exists to reduce the logging cost? Okay, that's a good question, but that is also dependent on the mostly supported formats that are there in the log management servers. Plain text and JSON are the industry standard for log management servers. There are some opinionated systems which are written to support some sort of formats in different data types, like Parquet, Avro, and all. But not every log management system supports. Queuing systems generally support such kind of format. So if you are, let's say, using XYZ queuing system, that may support you having logs routed over Parquet or Avro. But JSON is the common logging format for most of the front end tools wherein you have the ingestion done. uh, Okay, a little bit slow pace. Okay, I am going a bit fast in speaking, so I can slow down a bit. We still have an hour, so we can cover the two labs. I'll slow down from now. Thanks for the feedback. Uh, the next question is, when using cloud providers for AI, who controls the logic on how it's called calculated? Do they share the logic with the user? As part of observability, what are industry best practices for monitoring, restricting token cost count from cost perspective? So it's very subjective question, I would say. The provider cost is essentially calculated based on different aspects, including what all services behind the scenes are running, uh, what kind of computation it is, what kind of media it is. Image related computation is going to be less expensive than the video computation, which might be comparable to the audio computation, right? And the text computation might be likely the cheapest of all the four options. So it is essentially a function of how a provider has written resources, what kind of databases they are using. So let's say I am a provider and I am using a self-hosted MySQL server for doing some sort of computations in the background before I provide the results to you. Then in that case, it's self-hosted, so I might be running it in an optimal manner, and I might be saving a lot of cost in running MySQL. But what if I go ahead and I change my self-hosted MySQL to something like a vendor-provided SQL? Now, vendor-provided solutions are generally more expensive because they have some SLAs attached. because they are taking away the headache of you maintaining the server's reliability, and they ensure that the servers are able to perform under load for good amount of time. So generally locally hosted solutions will be cheaper than the vendor solutions because of the additional benefits one gets with the vendor solutions. And if I have implemented, depending on some particular vendor, my solution, naturally my execution cost will go high. So my solution, which is executed against MySQL self-hosted, will be expensive, will be cheaper than the one wherein my own solution is using a managed database server from a cloud provider. So there are multiple aspects to how the costs are getting calculated. Not everyone exposes, mostly people don't expose the dynamics behind calculating the per token usage cost, but they will give you understanding as to how a particular media will be getting treated. Like when I use x number of tokens in a particular duration, how much cost I'll be having. And sometimes it's a tiered execution model as well, because if I'm using semantic caching and I am having text based inputs, and I have implemented a question answer system, and my provider API is essentially for the question answer system, if I have only 10 tokens getting used over a week, then it's like I will charge the user more. But if I have 10,000 tokens getting used, out of which only, let's say, uh, 5,000 are making to my system, because 5,000 tokens, the queries corresponding to 5,000 tokens were semantically cached and served from outside my server, then it makes sense to provide a cheaper alternative. So I would say it's a tiered model. For first 500 tokens, I charge the user $10, but for next subsequent, let's say 2,000 tokens, I charge the user $5 only. So that's also how the tiering works. It's something which is not really transparent from the providers, but there are a lot of dynamics, like even including the usage or the applicability of constructs like semantic caching, or at the inference level there are more uh, techniques like kv cache utilization, hit ratio, etc. Lot of things go behind the scenes to come up with the cost. It's not really straightforward. Like if I go on, I can give a lecture for 4 hours just on the different factors on which the cost can be made. So it's a pretty vast, I would say, when it comes to that. Thanks for all the questions, and I'll ensure that I go a bit slow. Still, if you feel like I'm going fast, please do call out in the chat, and I'll be keeping a watch. Yeah. All right. So, lecture number two is uh, yeah, lecture number two is around the distributed tracing aspects, and here we are going to use a system called Arise Phoenix. Uh, we have seen people using things like LangChain tools like Langsmith and all. There are Langsmith, LangGraph related visualizations that you can go with, and you can have distributed tracing using Langsmith and all tried. Also, there are tools like Jaeger, Zipkin based visualization dashboards that you can go with. For this particular lab, I'm showing you a solution which is called Arise Phoenix, which is locally available through open source, and it can be run on virtual machines, can be run on Kubernetes containers and all. So that's why it makes a good candidate for us to try out in this particular lab. Again, make sure that your Jupyter notebook is essentially set with the right interpreter. And first, we need to understand what distributed tracing is. That's a concept which not many people understand, because most people have the view that observability is just logging and monitoring and nothing else. So assume that you have a call being made to some service. That service is essentially getting treated as a tool in your agent ecosystem. So your agent is making a call to a tool called ABC. This is the same example that I'm repeating that I had in the previous lecture. This ABC tool is having some degraded performance because of some dependencies or issue at its side, or probably it has got some more traffic than what it could tolerate. Now, this particular ABC system, which generally takes 200 milliseconds to reply, it is taking 5 seconds to reply. Because of which, your own agent is now not able to performantly cater to your customers. So, overall, your agent was able to earlier respond in 800 milliseconds. but now it is 5 seconds plus x number of milliseconds, so roughly 6 seconds you are taking to respond to your user. Now that is where users start complaining, and you get a lot of support requests that your agent is down. However, the case is your agent is not down, the upstream service is down. So that's where, being a person who has to deal with reliability of the application, you need to understand where the bottleneck is, whether it is the right time to switch from service ABC to service EFG, which is a fallback service and is still giving me responses under 200 milliseconds, is the decision you will make only after observing the things. And that's what the site reliability analysis looks like. So I have, let's say, service ABC, which generally takes 200 milliseconds, and I have a service EFG, which is just a fallback service of ABC. That service takes, let's say, 250 milliseconds, but it works and it is also reliable. Now, when I am loaded on ABC and ABC is giving me 5-second worth responses, I certainly need to analyze what is the culprit in this whole ecosystem. And if I am able to recognize that, okay, ABC is the culprit for my degraded performance, I can make a switch either dynamically or by taking a call after analysis that, okay, I want to start routing my traffic to EFG because I know service ABC is not going to recover within X number of hours. And I cannot really afford to have my users receive the responses in, let's say, 6-second worth window, when my agreement with the customers or clients is that I'll be serving the responses within 1 second. Okay, so this is where distributed tracing comes into picture, wherein you put a tag, let's say, on your actual transaction that has hit your system, and that tag propagates across all the transactions being conducted from your system. So it's like, call from my service to ABC will actually be tagged, and I'll be able to recognize the output of a service based on that particular tag. So that means if ABC is taking 5 seconds, I'll know because of the tag that it is taking 5 seconds. So it's like a system, a chain that you form, and this whole chain we call as a trace. So, and for a particular transaction, the end to end latency analysis, the end to end analysis of what all other performance indicators are there, is essentially called as trace information. And every independent transaction that is happening, like the response of performance from ABC, is called a span. And ABC further could be having some sub services or upstream services which it might be interacting with. So ABC itself could have child spans in it. So basically it's a parent trace under which you have some spans. Spans represent the individual transactions that are happening, and those transactions can further be broken down into child spans if you have that kind of nesting hierarchy. And that is the whole kind of meaning of how the distributed tracing thing works. Uh, so so we have to understand at which point, in which transaction, how much time is being taken, what are the indicators of performance, etc., which are being captured as part of such transactions and the inter transaction calls. Okay, so the first thing is, we will be launching the Arise Phoenix system. In order to launch the system, you just need to go ahead and, after you are done with installing the requirements, you need to do Phoenix Serve. When you do Phoenix Serve, you will have a system uh, like this, basically spitting out logs and telling you, okay, I'm running, so this is like Phoenix server which is running. It shows that your traces are going to be served on port 6006 for HTTP, and when you are actually running it in gRPC mode, it's 4317. So I'm using HTTP mode, so my traces will go to 6006 port. And then it goes ahead, it has some health check related things also, and this is how the dashboard looks like. This is the landing page of Phoenix which I'm kind of running, and this has got a bunch of traces. Some of them are diagnostic traces, so every x seconds or minutes I'll be having a trace span which will be doing some diagnostic information shipment. That is something which we really don't need to be worried about. It's just telling that, okay, my service is up, my diagnostic status shows that I am verified with the traces being synced to my service. We'll see how actually the things happen. So before this, You would have heard of terms like open telemetry, open tracing, open sensors, and so on. There is a difference between all of them, and we need to understand which one we should be using in today's scenario. So, generally speaking, open telemetry is the industry standard as of now. Open tracing and open sensors are ones from which the industry is moving away, because open telemetry is now supported under Cloud Native Computing Foundation. So it's an initiative under CNCF, as we call it. And CNCF is generally a body which has solutions, a lot of incubating solutions, graduated solutions, solutions that are to be graduated, etc., covered for distributed system architectures and container based architectures, and even virtual machine deployments or bare metal deployments. So it's kind of a body which has a lot of tools under its landscape, and these tools are generally open source tools, mostly open source tools, but some of them are provider specific tools as well, so they might have some tiers available from service level experience perspective as well. So open tracing was a format, I would say, standard, which was exclusively for capturing the trace information. And the flaw with that was that it was just having API specification exposed, and there were no SDKs to work with. And then there came open sensors, which was another standard which had both metrics and traces exported. It was open sourced, and it had SDK libraries as well. But then people really became confused that, okay, whether I should be going with open tracing, I should be going with open sensors, because open tracing required one to actually have specific implementations for vendors written. Open sensors, because it used SDKs, it was still okay, and it was working without any vendor kind of dependency as such. So there came a standard open telemetry which was taken under CNCF, and this particular open telemetry standard supports tracing, metrics, and logs, all of them as kind of a centralized unified framework. And you have SDKs exposed, and you don't have to be vendor dependent. So if I'm having my traces as per open telemetry standard getting exported, whichever management trace management server supports open telemetry based ingestion, they will be able to take my traces as is without any modification. So that's the beauty of it. And that's where we will be also focusing on open telemetry, and we won't be going with open tracing and open sensors, because the industry standard today is open telemetry as we speak. It might change in future. There are a lot of things in observability that are happening, but yeah. So you can run Phoenix using Phoenix Serve as I showed, or you can go with Docker implementation. And here for gRPC, we are exposing 4317 and 4318 as well. And there are different kind of systems to which we can expose the open telemetry related traces that we have. I'll be using Arise Phoenix, but if you want to go with any other open source alternatives, you can go with Jaeger. This is also a tool which has existed in industry for quite some long time. And Langfuse has open source version, but it does have some, I think, proprietary version. It is called Langfuse Cloud, if I'm not mistaken. So it's up to you which one to use. We'll be using a Rise Phoenix, and I do have the code for Jaeger also in the same. So in case you are running Jaeger, you will be able to run. The first thing is to have the tracing server initiated, instantiated, and then we just need to ensure that it is able to send the traces. So we are just importing some standard libraries which are there for importing Phoenix and open telemetry related stuff. Why these open telemetry libraries are required is because we have the trace span shipper or the trace provider related initializations to be performed using these libraries. So I'm choosing tracing backend as Phoenix. You could have chosen it as Jaeger because I have configuration for Jaeger also here. I'm using Phoenix, and uh, I have exposed the check of whether the port is in use or not. I have already spawned the instance for Phoenix, so it's already running on 6006 port. Had it been the gRPC use case and all, we could have gone with the 4317 port and so. But intentionally knowing it's HTTP only, I've kept it 6006 for simplicity purposes. So basically, what we are doing is we are just creating the central trace provider, instantiating it, making sure that the provider Phoenix has been set for the trace provider library, making sure that we have also set the export endpoint for the 6006 v1 traces so that all our traces are routed to this particular endpoint. And also, we have introduced the synchronous publisher for span. Synchronous publication again is something that is debatable. Generally, with logging and with tracing, it's better to go with asynchronous implementation. For simplicity purposes, I'm using the existing simple processor class, which is using synchronous publication mode. And then I am registering the tracer as agent observability tracer so that it is convenient for me to filter ahead in the solution in the tool, in the Arise Phoenix tool, where the observability stack is. So I just went ahead and executed this, and it gave me the trace provider configuration being already connected because of a local instance running. Now, what we are going to do is we are going to have the open telemetry implementation done. So we are going to simulate two tool runs, one for web search and one for calculation. And again, I have mocked these up so that we can keep things simple and we don't have to rely on any licensed version. The the thing is with open telemetry, and we'll come to this particular production security note, etc. shortly. Uh, uh, so we'll come to the implementation of this directly first. The functions, the tools that we are writing are essentially having their own span attributes, which means the attributes which are going to show in the trace sessions, pretty much like how you would treat key value metrics. These are key value pairs of attributes that are there as part of the trace so that you can do some filtering, aggregation, reporting on these traces. I can have as simple trace as HTTP status code equal to 200 or 500 or something. So I'm doing a tool name so that in my trace body, I have this attribute with the web search tool name identified. Then I'm doing the tool input, which means I'm logging the query that is there. And I'm doing a query kind of related manipulation just to make sure that tool output is also fed. I'm just mocking up the output for this particular run, as you can see. And in the calculator one, again, like I'm simulating a calculation. So a string will be passed like what should be what should be two times multiplication of the population of France, for example. So that is where I have the tool registration done. I have written some expression logic to ensure that I'm sanitizing my input, removing any unnecessary characters, and I'm just ensuring that I'm having the exception handling logic for the result that I'm putting in the expression. So these are the tools that we will just instantiate. So these are function call, function declaration. So pretty much they will execute quickly. Now we are trying to simulate the reason and action loop basically. So this is the react or the plan and solve kind of loop. What we are going to do is we are going to have this function run react agent. This is going to mimic the loop for us and essentially is going to prepare that trace session for us wherein there could be parent spans and child spans, etc. And we are going to do a bunch of iterations so that within the iterations we can go ahead and we can see how the things are going to look like. We are registering the parent span as the agent query so that we recognize that at the top. And then we are just making an LLM call by using the LLM client that we are instantiating, again backing to the two examples that we had in the source file. Here we are just starting the tracer with the context manager, and we are saying that for any calls being made for the LLM client, we are going to have its responses fed as part of the trace attributes like we were doing above. And likewise for the answering thing, we will just ensure whether the final answer is there or there is an action like calculate x times the result, etc. So I'm having a keyword based regex implemented. If my response contains final answer, then I'll treat it like a final answer and feed it to my system, and I'll finish the query and I'll return the output. If there is an action that I'm simulating like multiply the response by two times or so, then the action related action match else case will the conditional will run, and it will make a call to the search tool or the calculator tool depending on which tool name the action has called. So it's like pretty much simulating how systems work behind the scenes. I'm just giving a very simplistic example of two tools being executed in conditional manner, but the production systems are much more sophisticated. So this is not really a production implementation. This is for explanation and educational purposes only. And ultimately, if there are any malformed inputs, then we report them, and then we say that okay, we have logged the traces and we are okay, the agent has kind of timed out, etc. We return the response. So we will instantiate this, and again it's kind of a static declaration only, so it has got instantiated. Now we will go ahead and we will run our actual query, which is going to simulate the cases that we have put in the conditional. So I'm going to put a query like what is the population of a particular country. I'm going to ensure that the traces are collected for this particular thing, and then ultimately I'll just return the answer. Let's execute this. It's executing multiple iterations. As you can see, we had I think counter of up to 5, which means 4 iterations. Yeah, okay, 3 iterations maybe are there. So the first iteration was I need to find population of so when I said what is the population of France, it went ahead into a react loop using the logic above. It thought that okay, I need to first find the population of France, and then it searched for population of France. And because it was a web search tool, it went ahead and did the tool search, searching for France population, and the tool responded okay, the population is 68 million. Then because it got the output of the first tool, it went ahead and then it had another thought, the population of France is 68 million, now I need to multiply this by 2, because the actual prompt was population of France multiplied by 2. Okay, so then it interpreted that okay, it's no longer a web search tool call, I need to make a call to the calculator. So it went ahead and did a 68 million into 2, and for that the calculator evaluated some figure. I'm not sure if it's mathematically correct, but seemingly it looks like. And then ultimately it is giving the output to the user that okay, the final answer is the population of France is so and so. And now if we go to the trace sessions, you see that the agent run span is showing. And this particular trace, the parent span, that is their agent run, it shows the final answer as what we returned from the query. But then the calls that it made to the tools and the LLM calls that it made are also kind of written. So we will click here and we will understand what the attributes were reported. So the first thing was I need to find the population of France, and action is search population. So it had 23 tokens basically for this particular query. And then the cost of the calculation was this, because we are actually calling our initial function of LLM response, and the prompt was this, and the prompt token were 31. So it made a tool search call, which is shown as this. Now you see one interesting thing here. If we click on this particular trace, it shows 2-second latency, which means this call to agent took actually 2 seconds round trip. There is a unique identification ID for this particular trace, which is the parent trace ID. Then this particular trace ID essentially has for its own child spans the different dedicated IDs. So this is the parent span ID, which took total 2 seconds. But within 2 seconds, how the 2 seconds got computed? The LLM call took 378 milliseconds and was identified by this particular ID. Then the tool search actually took 500 milliseconds. The next call to the calculator one actually took 236 milliseconds, and the tool calculator itself took 300 milliseconds to compute the 68 million times 2, and so on. And it finally returned the actual result and the cost attributes, etc. So now I can see that okay, if the tool cost, the tool calculator tool or the ABC tool in our original example was taking earlier 300 milliseconds, but somehow now it has been reporting 5 seconds, it's the right time for me to take a decision to either circuit break that or go to another tool or so on, right? So that's where I can analyze the trace, and I can kind of understand the actual flow of what is happening behind the scenes. It's pretty much like profiling your functions in standard traditional computing, but it's like a cross thing. It's beyond your application, what the other applications are consuming in terms of time, etc. There are some tips for navigating the Arise Phoenix UI. You can go through them. I think, in interest of time, it's better to go through them offline. But I have already explained you where the positioning is for the traces, etc. And then there are some production guidelines that we need to go through. But before getting to production guidelines, let's go back to the section that we skipped, which was this production security note. So essentially, we know, and it's a concept again that I am introducing, which goes a bit further than what we have actually planned for. But this is an industry thing which a lot of practitioners also is not aware of. So I would like to highlight this. Uh, there is a concept of shadow APIs, especially when we are talking about AI systems. Shadow APIs are available in traditional systems as well, but then more exploits are possible when we talk about AI systems. So, what exactly are shadow APIs? APIs which are present in your ecosystem somewhere deployed, which you might not be really keeping an active track of. Maybe you are using V1 version of API ABC, and that version has already got deprecated, but you are not keeping a note of the upstream APIs, and hence it's a shadow API for me because you don't really know what the contract with that particular API is, and you are not really actively tracking that. Or it could be from AI perspective, a scenario wherein you are using a web tool, uh, basically to make calls to external systems to be able to get responses. These are calls being made over network. Certainly some of the payload is being interpreted from the prompts that you are having, and then it's being sent to the other tools. Now calls being made with different compromised, let's say, parameters or URLs that are getting constructed on the fly in malicious manner are the tools, are essentially the calls which are shadow API calls for me. And these shadow API calls can be very harmful if they are essentially uh, made with an intention of doing some sort of malicious attack. And attacks can be poison attacks or hijacking attacks or injection attacks and so on. So that's where keeping a track of shadow APIs is very important. Keeping a track might be bit difficult because you will be requiring an active catalog to be maintained. So what better things you can do? Only the trusted set of sites that you support in your ecosystem, you can only allow list them when the call is being dispatched from your agent to the external ecosystem. That means you use a system, a filtering mechanism which sees, okay, the URL is abc.com, then I will restrict the call because it doesn't belong to the allowed set of uh, 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 sites. And that is the regular forward proxy kind of mechanism that we use. So in local or bare metal systems, you can have it using IP tables or the firewalls, UFW. If you are using virtual machines, you can go with security groups plus some sort of forward proxy appliances. There are appliances available at hardware level as well as software level available. This is something that you need to be aware of. Software level firewalls and forward proxies are available as well as hardware level are available. People who work with data centers and private data centers especially are very well versed with the hardware firewalls for such kind of use cases. So in case you want to understand more about hardware firewalls, you can start reading about Palo Alto firewalls or F5 firewalls or some firewalls at the data centers which can be installed, etc. Then, if you're using a serverless function as service or platform as service services, you can have the again NAT gateways configured. Sometimes some cloud providers have forward proxy related functionality baked in into NAT gateways these days. Some of them don't have, so you might have to leverage firewall rules plus service controls plus enterprise boundaries. Different names for different cloud providers are there. Sometimes the purpose also differs, but mostly these will be the set of tools you will be looking forward to. In Kubernetes, you can have network policies. You can also use advanced tools like Cilium, Tetragon, and all. Those are like tools which can help you with ingress and egress advanced policies on top of the regular network policies that are there. If you are having some unified gateway, then in that case, secure web proxy or egress forward proxy or even tools like Envoy or Squid, which can act like forward proxies, can be leveraged. So it's like a good thing, a good production practice to exercise when we are dealing with systems, not just LLMs. This is also applicable for traditional compute. So coming to the other production guidelines, we need to understand that open telemetry collector is there, which asynchronously will be kind of running in production. You should not be having synchronous spans, as we talked about. The other mistake which I see people doing quite a lot, or just due to lack of understanding, is that they think 100% tracing is going to help them. If you have 500 calls and you are doing 100% tracing, it's still okay. If you have 50 million calls and you are doing 100% tracing, it's essentially overloading your system with something which is going to impact the performance of your application as well, because traces are essentially part of the logic only, as we saw. If you have more tracing being done, you will have more injections of the trace code or the operators, etc., in your code, and hence your actual performance of the application will also get impacted. So tracing and logging should be done asynchronously. That is like one key takeaway. You should not be doing 100% of tracing. Generally, in production systems with high volume, 5% of tracing is good enough. And there is something called as tail based sampling as well, which means we drop all the traces which appear to be normal or have normal responses. We only have tracing done for requests which were anomalous, probably which resulted in some 5xx errors, or which resulted in higher latencies. So we can have the threshold set and we can do the tail based sampling to filter out all the normal calls and do the tracing for only the ones which contain errors or are anomalous looking calls. So tracing takes a toll on the performance. Please do tracing in limited capacity. 5% of 50 million is too much as well. So you need to understand that 100% tracing should never be done in production systems. It doesn't really make any sense. In your pre-production or testing beds where you want to do performance testing, go ahead and do 100%. But in production systems, it really doesn't make sense. Rather, it will deteriorate your performance. That's something that you need to understand. Uh, then span level payloads, you need to understand that spans, essentially like the attributes that we see, are what are going to also be vulnerable to high payloads. It's better to keep less characters in the output of your span keys that are there. So there should be some sort of truncation or deterministic hashing kind of approach, wherein you can have less sized values for your attribute keys that are there. So that is another production practice that one should be following. All in all, so far we have seen the logging and tracing. So next is the time for metrics, profiling, etc. Before that, I'll see if there are any questions in the chat box. Okay, so far, what role does API gateway like Kong play in observability? It is recommended to use them at client side or rely on cloud providers, AI gateways. Some examples of best use cases. Okay, a pretty good question. Thanks for asking. We need to understand that there are two aspects when we talk about API platforms, rather, three aspects. Uh, One is that we used to have a lot of traditional servers like Nginx, etc., which used to work like reverse proxies. Okay, so there is something called as reverse proxies, and then there are advanced API management systems. API management systems are essentially ideating from the reverse proxy concept only. That's the foundational understanding of how the systems have evolved. So we used to have something like Nginx, wherein we could do the HTTP header based routing, or path based routing, or query param based manipulations, and so on. So reverse proxies are themselves, I would say, Nave Man's API platform. When I say platform, I'm saying platform because platform can be of two types. One can be a gateway type platform, one can be a management platform. So there is a difference between API management and API gateway. API gateways are generally going to provide you with functionalities very similar to reverse proxies, but probably a bit advanced than them. And these are going to be for tracking the logic as to the manipulations that are to be done with respect to your API. Like I want to convert from XML to JSON the payload that is coming, or I want to do the API query parameter related checks. Like I'm passing the API key, whether the API key is authentic or not, right? Such kind of checks I can do in API gateway. When I do API management platform related discussion, it also talks about things like how I can monetize the APIs, how can I look at the performance of the APIs, how I can have a full life cycle wherein API registry can be maintained and shadow APIs can be identified for the ecosystem. So that is something which is beyond the regular gateway related transformations of API payloads that you are performing. And that's the main difference between reverse proxy versus API gateway versus API management. That API management focuses on the full life cycle from a developer perspective. For the API, it encompasses developer portals, it encompasses monetization aspects, it encompasses aspects related to API registry, shadow APIs, and whatnot. Not many API management solutions exist in the market, but generally API management solutions are for full lifecycle stuff. API gateways are for transformations, and reverse proxies are generally ones which used to be traditional systems which evolved into something like API gateways, but they have their dedicated roles as well for ingress. That is again beyond the discussion of this particular topic. It requires its own dedicated talk. As you talk about what role does API gateway like Kong play in observability? So first we need to understand is that API gateway and observability platforms are two different things. API gateways have an aspect of observability embedded, which means for a particular API transaction that is happening, you will be having API level observability stats reported in the API gateway portal likely. So there will be API transaction related telemetry and observability window in your observability in your API gateway platform or UI, which will tell you that okay, your transaction took 500 milliseconds. They may be having features like doing distributed tracing, or they may be doing a naive man implementation like a start time minus end time, how much time it took for the upstream systems to deliver the call, what time the call was received from the client, and what time the call was dispatched from our system to the client. Such kind of information is available in the API gateways from performance perspective. So API gateways do have aspects which can be leveraged for understanding performance of the API transactions, but they are not alone, because they cannot be used alone, because there is another category of observability that needs to be seen, which is called application performance monitoring, APM. So in APM, what you do is, so API gateway, what they will do is they will tell that a call is going at slash catalog API paths, and that path is taking 800 milliseconds. But within that path, what is happening is something the application performance monitoring system will be giving you understanding of. If you have tracing available on the API gateway till the nested level of the functions, then it might be that you get some function spans as well reflected in your API gateway, but not every API gateway has that feature available. So application performance monitoring along with API monitoring along with real user monitoring, which we call RUM monitoring, which is like first paint load time or first page load time or click rate, etc., which is how much time the user it took for the user to load our web page or load our agent let's say prompt system, and in how much time they were able to go ahead and click on the window and type their prompt and then dispatch the stuff. So such kind of real user monitoring systems, etc., also exist. There are advanced concepts like beacon monitoring and all, which are beyond the scope of this, and they end up into front end monitoring and UI monitoring related aspects. But yeah, like the question that you have asked is pretty relevant. Observability, this is really where I would like to again re-emphasize that observability is not really a function of just one tool that you are using, one particular stack that you are using. Observability really means anything and everything that is there from the client to the server to the third parties or the internal parties through which you are getting the responses back to the client. everything that gets covered in between has to be monitored in some or the other way. Even monitoring at the level of your internet providers, IP providers, is something that is part of observability, but that might not be your first primary kind of area to look into from observability perspective. People who really work with streaming a lot of videos or having streaming online games supported, they really track the observability at the internet provider level as well. They even check how much time it is taking for them to switch the network on the internet, so how the BGP related sessions are playing, etc. All those things actually come. Different use cases have different kind of observability metrics that are to be tracked. Hope I answered your question. But yeah, really nice question, thanks for it. Coming to the third one, which is the last one, we have 20 minutes, so I think we have decent amount of time. And since we are taking QA alongside, so I'm happy that we are covering your queries as they are coming. All right. So last section before we get to the compliance, security stuff, and all. And this is all about metrics, alerts, but then there is another dimension of profiling that I introduced you to at the beginning of the session. So first we need to understand that metrics essentially help us with performance monitoring. Metrics also help us with realizing where the performance can be degraded, like even at the IP provider level, there can be degraded performance, which is causing streaming issues, etc. So all those things actually come under the metric profile. And we need to also understand that sometimes the thread bottlenecks could be there. There could be bottlenecks at the CPU cycles of your application. It might be that the multi-threaded application that you have written is having thread contention, or it could be like a very common use case wherein you are interacting with the database, but the database has a number of connections available, which you are maintaining through the thread pool and the connection pool, but then the number of threads that you have spawned don't really tally with the connection, or the connection pool strings that you have are already exhausting the threads on the database. So there are multiple permutations, combinations that can be there as to how the underlying contention on the database connection pool or thread pool could happen. Again, like that is beyond the discussion of what we have planned for today. But you can understand that CPUs can become bottleneck. We can have resources like memory become bottleneck, and memory essentially is not compressible. So generally you would see an kill out of memory kill happening whenever there is a memory outage. For CPU, you will see thrashing, which means your process will start responding slowly. For memory, it will likely be an out of memory kill, or there could be segmentation faults if you have not really handled your memory objects correctly. There could be some sort of even garbage collection issues, pretty common if you are using a stack which has a GC collection related stuff as well. So you need to understand that heap, which is related to memory, can have issues. Threads can have issues. CPU can have issues. Uh, File descriptors, which I have not written here, can have issues. Number of open files that are there, number of connections that are open on your agent can be issue. Observability goes beyond what we are discussing today, but still we are trying to give you understanding of what all aspects you need to focus on, like file descriptors, open files, etc. I have not really emphasized on in this. They are again pretty much applicable to non AIML workloads. There can be performance bottlenecks because of these kind of things as well. At the client side, from AIML system perspective, you need to understand that time to first token is generally what people focus on, like how much time it takes for the very first output response token to be fed. And then it sees how much is the inter token latency, like how much is the time between the subsequent generated tokens being rendered or being put to the output. And then what is the end to end latency, like how much time it took for the request to come, the whole round trip to happen, my agent invoking different tools, it gathering responses, aggregating them, sending back to the client, etc. And the network overhead for sure, which is something which we don't have much control over, but can be a party to the issue. And then server side performance, which we have covered to some extent by talking about semantic cache, etc. But then there is something called as KV cache utilization and hit ratio as well. That is kind of an important aspect when we are talking about inference serving. So this is where you have for like a particular server in which you have some computation happening, you might be having the token computations being cached on that particular server, so that for a particular key what the next probable word should be or what the output should be is getting cached. Like there can be different variations to this. So if I have a KV cache which is thickly populated with the terms related to semantically similar queries, if I route request back to that particular server, then generally my response will be fast because I already have some key value pairs matched. And if my query has to respond in the quick brown fox goes and so on, it in the next response as well, it will be pretty quick for me to retrieve the results from the cache and return to the user. So that is where there are advanced concepts like KV cache and all, again, which we cannot cover in detail in this particular session. But observability around the KV cache ratio, the utilization stats, etc., also forms the server side of performance observability aspects. So today, in this lecture 3, we are actually covering about such kind of stats that we can retrieve from the systems, and we can leverage open telemetry for metrics, is what I have already told you about. We will be using things like counters and histograms to reflect how many number of instances or counts were there for agent run or the errors which were encountered. Histograms are generally spread over time, so it will be like token counts per request, or there can be a time average time for token, or some sort of other response related latency, etc., computation related latency getting reflected over histograms. So we will be using an in-memory metric reader. In-memory metric reader means in the Jupyter notebook, we'll be able to have the metrics read from one section and propagated to another section in the subsequent cells without any issue. Generally, the metrics which are open telemetry metrics in production are using things like a pull model reader or a push model reader or exporter. So Prometheus metrics essentially have a reader model wherein you can pull the metrics. The endpoint slash metrics is generally exposed for applications to scrape the metrics from Prometheus. And there is this Prometheus agent running, which is actually polling, and then it is aggregating the metrics, and then it's dispatching the metrics to your management server. Likewise, there can be a push model wherein generally you are having your application push the metrics to a particular endpoint. Again, agents could be there which could be collecting this and then could be passing in asynchronous manner the metrics to some other party. Or it could be that you are directly having an in-house a metric server getting run, and you are having push model for pushing the metrics to that. Again, the metrics can be pushed over gRPC or HTTP or other sort of streaming protocols. Again, that's not something which is in scope for this particular session, but an important point is that when you are using something like a function as service or platform as service, generally you would be using a push model than a pull model, because it really depends on the life cycle of till when the function will be available. If I know that by the time my exporter goes ahead, clocks the next cycle and has to pull the metrics, I will rather go ahead and do a push model, because I don't know whether my function will stay for the next cycle to clock in for the slash metric pull model, right? And then console metric exporter is for STD out related serialization. It is something which is used for local testing. We are not using it. We are just using the in-memory one, which will support us with the in-memory runs. The first example that we have is for a C profile. This is a Python written library, which is going to give you the profile for your CPU usage and all. So we are just having an in-memory telemetry reader getting instantiated. Again, just putting the right set of headers, etc., to be able to kind of relate to, okay, these are metrics from the agents. We are setting up some sort of counters like number of total runs we are instantiating. We are instantiating the create counter. We are instantiating a histogram which will give us the distribution of the LLM response latencies, and then the accumulated cost for the LLM. So we will go ahead and instantiate this, and we will see that it's pretty simple, straightforward. It just tells that the counters and the histograms have been spawn. Uh, so metrics are not visible in the Arise Phoenix that we are having. So basically, these are in-memory metric reader related metrics that we are leveraging, and we are not really pushing them to Prometheus endpoint, so they are not available in Arise. But there are kind of uh, metric exporters available that are available in system which can have this particular portal also get the metrics. So what we are going to do is we are going to again use our LLM client response model, and we are going to have the metrics essentially calculated. So we are having the metric calculator logic now run here. We first have the start time of LLM reported. We take the latency of the LLM reported by doing the computation of the current time minus the start time. In between, we have the prompt which we are actually invoking. So it's pretty much like a time function that we saw earlier. Then we are having the histogram. This is essentially a histogram over the LLM latency. And this particular histogram is essentially captured for the run so that it can just be a point in the graph that we actually get. Likewise, the cost counter is essentially retrieving the cost from the response, and then it's updating the counter with the actual value. And then we do have some exception handling related kind of logic as well, very name one, and we are returning the kind of response here. We'll execute this, and we see that we are just having this function instantiated. Next is what we will run a bunch of queries against the function that we have instantiated to have the simulation of the traffic done. And we are just going to throw the metric related output in form of readable report. I have implemented it very simply by using nested for loops. These many for loops are not good for your production code, so please avoid this pattern. I have just for sake of simplicity gone ahead and reflected that how much is the total cost, etc., getting reflected, the sum of the LLM response latencies and the accumulated cost, etc., across different runs. Like there are different kind of queries that I have run. You can see that evaluation is happening to correct for the first three queries, but the last one is a simulation of a wrong case, so it's kind of a false query evaluation that happens. That was done intentionally to ensure that we have LLM as judge sort of functionality also reflected in this particular demo, though it doesn't really uh, directly influence the observability related discussion that we are having right now. Then coming to server-side polling, profiling, thread dumps and memory audit. So we will show you kind of the C profile thing for CPU runtime execution. We have already discussed about the different handlers that are there. In Python, we have the C profile or P stats, which can be used as modules for the CPU profile. Likewise, for thread dumps, we can use JStack or fault handler. For heap dumps, we can use the trace malloc related function and so on. So we have a function slow agent test, again jittery, but this is like sleep, which is deterministic that we have put, and we are just showing a profile for this particular function. So we will invoke the we will initialize the profiler, we will invoke the function, and we will stop the profiler, and then we will just show the metrics that have been collected from the profiler. So I'll execute this, and it will show us some table. So basically, how to interpret this table is quite interesting, because this is how the C profile looks like for any particular function call that you do. Within a function call that we actually made, there are 1018 actual nested function calls that are happening, the system calls that are happening, etc. 991 primitive calls means the calls that have not got any recursion done. So which means there were 1018 minus 991, whatever the count is, around 20 calls were there which were recursive calls. And how to read this table is pretty important for you to understand the number of times the function was called. Which function? Built in method time sleep, which means time sleep was called 2 times during my call. And over the two calls, the total time it took was 1.183 seconds. And there is this cumulative time which is also reflected, which is time including all the subfunctions of the function being referenced, which means this particular function did not have any subfunctions because the total time and the cumulative time are meeting, like exactly matching. And per call essentially means divided by 2 that we did. So basically 1.83 divided by 2 is per call start. And yeah, that's pretty much. So basically here you can see that the most of the time that is going is in the sleep function only, because per call is 0.592. But if you go ahead and do CPU profiling for a particular function, and you see a particular nested function in that, or a system call taking a lot of time in the per call thing, like you can sort this by that, then you can go ahead and inspect what exactly the problem is with respect to that function. Okay, so that's where the CPU profiling becomes quite handy even with the AI ML systems, because nested execution many times has this issue wherein some sort of CPU leak is there, or some processes unnecessarily hogging the CPU cycles. All right. So last is the alerting rule thing. So I have implemented again a Naveman alerting system by writing a function at my side, doing a threshold definition here, which says, okay, the alert threshold second is zero point 0.5 and the cost alert threshold is $0.003. If I find from the metrics collected above, if my latency or the cost goes beyond a particular value, then I just throw the number. So for now, everything is looking fine for the different runs that I have done. So it's showing green check marks. But ideally, you would be invoking a function to alert manager, or a call to your, let's say, status manager or incident response manager, that okay, you have breached the threshold, and hence you will be getting some sort of on call thing. One aspect which we will be covering on coming Tuesday is around the sandbox ecosystem. This is where the AI agents that have the execution done, how their internal runtime execution runtime can be made secure. So we will park this for Tuesday's session that we have on VASM and the sandbox runtime, gvisor related details on agentic systems. We'll come to the production guidelines for this particular session before we get to the main ones. So metric collection, again, better to keep asynchronous alert manager or alert routing you can do with tools like PagerDuty, Opsgenie, Alert Manager, or if there are cloud provider related tools that you are using, you can use them. There is a need for having profiling done for your CPU as well, but then there will be kind of overhead, performance overhead as well, because of the CPU profiler getting invoked. So again, this is very similar to tracing. We should not be having C profiler run continuously on all the calls. uh, you can rather have agents which can scan through your calls. So Pyroscope is there, Google Cloud Profiler, they will sample your production calls and they will make CPU profiling outputs available to you. Likewise, for memory dumps and thread dumps, there are profilers available. And you can actually generally do the memory dumping and the thread dumping as part of your pre-production exercise. So we'll come to Notebook Zero, which has the overview and the key takeaways for every session that we just talked about, given we have 2-3 minutes only. We first talked about how the application performance monitoring for traditional applications versus LLMs versus agents differ. Agents generally we are treating here as the non-deterministic singleton stateless LLMs, and agent observability we are treating as the stateful execution loops wherein you are making multiple calls to tools and all. Then we talked about the FinOps aspects and the GreenOps aspects, and we also talked about how you can determine which data centers should be executing what kind of tasks at which time by using some upstream query APIs like what time and electricity map. We also saw that semantic caching can be actually giving us a boost in terms of performance. We talked about using the sparse JSON schemas with dynamic logging and containing the logging levels just to ensure we are not polluting the log space. Then we talked about open tracing, open sensors, and open telemetry, and ultimately we resorted to go with open telemetry. And we also saw how with open telemetry we can deal with metrics and the traces. We then had a look at the KPIs, including the client user experience and the server side stuff. Some advanced topics we touched upon, like KV cache and all, but we couldn't find time to go into details. Then we finally wrapped up with the thread dumps, profile dumps, and heap dumps, which are again very useful, but people generally don't focus on. These are some of the aspects which you should be getting into when you see your agent not responding and going into circles and not really even for 15 minutes responding and then getting into a timeout. Generally, there is a thread or memory issue in such scenarios. These are some of the aspects that we should be kind of focusing on from deployment strategy perspective. So agent deployments, when you are doing over virtual machines, you could be having standard process managers like systemd, supervisor d, or process management used. And for telemetry, you can go ahead and use the regular JSON logs. The logs will be written on the file system in the virtual machine. You can use a log forwarder like fluentbit, ship the logs to Grafana, Loki, and you will be okay. When it is Kubernetes, you need to run some collectors as daemon sets on Kubernetes, or you can even run log forwarders or sidecar containers. It generally depends on the architecture of application what you should be using. When you are using the serverless platform as service applications, generally it's a push model that you go with, because these are ephemeral containers that will go away, so you won't get time to poll them. When coming from operational health perspective, like, this is one of the points which not many people focus on, but I highlighted in the start. If your application itself is not ready, like your agent is starting but the agent has to interact with database and it is not able to form connections, the agent should not be treated as a healthy agent. So readiness probes and liveness probes for your upstream downstream applications should be configured. Generally, people who have worked in Kubernetes area will relate to this, because Kubernetes by default from design perspective has liveness probes and readiness probe related constructs exercised. And this is kind of an advanced note on the data observability, how to have data lineage, freshness, etc. also tracked. So this is like something that you can read offline. For people who are very kind of enthusiastic about observability, please do check out a project called EBPF. It's called Extended Perclip Packet Filter. This particular project is now under Isovalent under Cisco, and this is part of CNCF as well. And this particular project has kind of zero instrumentation, auto instrumentation like features, wherein you don't have to write any code in your language. Directly your metrics or your telemetry information will be tapped from the system calls, the ones that are there in kernel that are happening, and you will get a beautiful kind of observability pane. There is a Grafana Bila tool which is available for auto instrumentation, which directly starts taking metrics and information from your underlying operating system's kernel, and then it ships the information and creates dashboards for you. So pretty good area to explore. On the governance side, we have already talked about the DLP stuff and the related sensitive data protection tools. There are some other aspects like model bias and drift monitoring, which relate to the data related stuff that we talked about. And then it's not just about what we just discussed, it's also about having security vulnerability tracking and threat management. So anything you are, any AI artifact that you are scanning, that you are consuming should be scanned. It's called content provenance and software provenance. So I actually gave a talk 2 weeks back at KivernoCon for how to have software provenance and content provenance exercised in AI with observability. So you can check that out on YouTube. That covers a lot of aspects that are listed here. And yeah, pretty much that's the end, and we are 3 minutes over than our scheduled time. But yeah, thanks for staying. And in case you have any questions, I can stay here for a couple of minutes. All right. No questions. I'll wait for a minute or so, and we can then conclude. But yeah, thanks a lot for being such a nice audience, popping up the questions. These were pretty relevant. I hope you learned something unconventional and not something which you generally find in textbooks. Uh, yeah. So over to you, whosoever is the moderator. Sorry, I'm just able to see EICT Academy as the moderator. Yeah.
Thank you, sir.
Yeah.
If any participant have any question, they can raise their question in the chat.
All right. Thanks again, everyone, and hopefully we'll see you on Tuesday then for another lecture around sandbox security and agents. Yeah. All right. Thanks. Bye.